Hey guys, and welcome back to another video on the channel. In today's video we're going to be evaluating this limit, so the limit as x goes to infinity of 1 plus 1 on x all to the power of x. Now, if you've ever studied Euler functions, you might have seen this limit before, and this limit is actually equal to the number e. So e is pretty much Euler's number, which is approximately 2.71 roughly. But pretty much in this video, we're going to be showing why this limit is equivalent to this number here, okay? So step one is all we're going to do is call our limit just some letter y or k or anything. So some constant pretty much, okay? Now once we call it that, what we're going to do is apply the natural logarithm to both sides. Now the reason why we're going to choose the natural logarithm is because later on when we use L'Hopital's rule, we can differentiate the natural log rather than any like log 10, log 5 or anything like that. So that's why specifically we're doing natural log on both sides, because later on we'll use L'Hopital's rule and we can differentiate the natural log quite easily. Okay, so ln of the limit of x goes to infinity of 1 plus 1 over x to the power of x. Now with logs you can bring this power down the front outside the log, okay? So hypothetically we could actually, if we wanted to, we could remove the limit and we could put it here and we could put the log and we could write it like this. So I'm just going to put the limit back now and we've got the infinity sign. So put the limit back now. What we can do if we wanted to is bring this power of x down the front. So we could write it technically like this. So the limit as x goes to infinity of x natural log of 1 plus 1 over x. Now we're not going to do this right now because this doesn't help when evaluating our limit, because if we would put in x is equal to infinity, well, we're going to just have infinity times some number here, which isn't going to help us. However, we can rewrite how x looks. So x is the same as 1 over 1 over x. So in other words, 1 divided by 1 over x is the same as 1 times by x. So if we want to, we could rewrite it like this. And it looks a bit funny, but the reason why we're going to do that is for L'Hopital's rule. So right now, this is the thing we have. Now we can't really evaluate this limit, because if we were to put infinity, we're just going to get natural log of 1 up here, and here we're just going to get pretty much a very small number. So we're going to get like a 0 divided by 0, which isn't that great. So what we're going to do is apply L'Hopital's rule. So Lop, so I'll just write L rule for L'Hopital's rule because I can't really spell it. Basically, is if you have the limit as x is approaching some number of f of x on g of x, then that is the same as the limit as x approaching a of f dash of x on g of x. So in other words, the derivative of the top and bottom is the same limit as a regular function pretty much. So all we got to do is pretty much differentiate this function and this function here, okay? Because they're essentially equivalent at this limit according to L'Hopital's rule. So what we're going to do is, alright, we'll leave this side here. So ln of y equals the limit as x goes to infinity, and now we're going to differentiate each of the terms. So the first one is differentiating natural log of 1 plus 1 on x, and the second term is differentiating 1 over x. So if I were to differentiate this term, it's going to be a chain rule because we have an inside function. So straight off the back, it would be 1 over this function. So 1 over 1 plus 1 on x times by the derivative of this inside function. So the derivative of 1 is 0, and the derivative of 1 on x. Okay, so if we want to differentiate 1 on x, we can write that as the derivative as x to the minus 1. So all we're going to use is the power rule, bring that negative 1 down the front, and subtract the power by 1, so you get minus 2. So hence we get negative 1 on x squared. So the derivative of natural log of 1 plus 1 over x is going to be this term multiplied by negative 1 on x squared. And then we're going to differentiate this, which is exactly the same thing as what we just did there. So that is -1 on x squared. So when we're rewriting it, we'll write it as the fraction as 1 over 1 plus 1 on x times by -1 on x squared divided by -1 on x squared. And hopefully you can see the reason why we've done this is basically those terms can cancel out now. Okay. So ideally we have natural log of y is equal to the limit as x goes to infinity of 1 plus 1 plus 1 on x. Now, as x goes to infinity, this term here is going to approach a very small value. So as x goes to infinity, 1 on x approaches 0 because you have 1 over 2, 1 over 4,000, 1 over infinity is basically 0. So we can basically apply the limit and get rid of that term. So hence we get natural log of y is equal to 1 on 1, which is 1. So therefore ln of y equals 1. Now ln was log base e, so log base e of y equals 1. We can rearrange this and go y is equal to e to the power of 1, which is just e. And remember, we called our limit y, so what we can do is say, since y is equal to this, we can then say, because y is equivalent to e, this limit is then equivalent to e. So if you were to plug in big numbers into this algebraic expression here, you should start to appear, what should start to appear is 2.71 blah blah blah, etc. Righto. I hope you enjoyed this video on the channel. Like and subscribe, and I'll see you in the next one.